Hello everyone and welcome to Control Engineering, Control Theory and Dynamical System tutorials. In these tutorials we present real and applicable knowledge of control engineering, dynamical systems, signal processing, optimization and machine learning. This particular tutorial is dedicated to the pitfalls that can happen when someone applies the linearization procedure to nonlinear dynamical systems. The main motivation for creating this video tutorial comes from the fact that people often tend to analyze the stability of nonlinear systems by using the linearization procedure. And there is nothing wrong with this approach. Linearization can be a useful method for analyzing the stability of nonlinear systems. However, I noticed that inexperienced students, researchers, or even engineers do not properly understand and apply a theorem that enables us to analyze the stability of a nonlinear system by analyzing the stability of a linear system. And consequently, they tend to draw wrong conclusions that can lead to devastating results. The purpose of this video is to warn you of pitfalls that can happen when incorrectly applying the theorem that enables us to analyze the stability of a nonlinear system through its linearized version and to teach you how to properly apply this theorem. First, I will briefly summarize the main ideas that will be presented in this video tutorial. Consider this nonlinear system. x1 and x2 are state space variables. And obviously this is a nonlinear system because of these two nonlinear terms over here. In this video tutorial, we will linearize this nonlinear system around its equilibrium point to obtain this linear system, where A matrix is 2 by 2. Next, we will show that the eigenvalues of this A matrix are on the imaginary axis. That is, they are over here. And this is a complex plane. Here we need to add that we linearized the original nonlinear system around the equilibrium point x1 is equal to 0 and x2 is equal to 0. That is, this linear system is an approximation of the original nonlinear system around this equilibrium point. Since the eigenvalues of the matrix A of the linear system are on the imaginary axis, we can safely conclude that this system, or better to say, the equilibrium point of this linear system is stable. And this is a correct conclusion. Definitely, the system is stable, however, it's not asymptotically stable. Now, here comes the error and pitfall that inexperienced students, researchers, or even engineers often make. They reason like this. Since the equilibrium point of the linear system is stable, this means that the same equilibrium point of the original nonlinear system is stable. Well, this is a wrong and incorrect conclusion. You cannot conclude that. In this case, you cannot draw any conclusions about the stability of the equilibrium point of the nonlinear system by analyzing the stability of the equilibrium point of the linear system. However, there are cases in which you can actually analyze the stability of the equilibrium point of nonlinear systems by analyzing the stability of the equilibrium points of the linearized systems. And these cases are the following. If the eigenvalues of this matrix A are over here, that is, they are not touching the imaginary axis, then you can definitely say that since the linearized system's equilibrium point is asymptotically stable, this implies that the equilibrium point of the nonlinear system will also be asymptotically stable. Similarly, if the eigenvalues of the matrix A are over here, that is, if the equilibrium point of the linearized system is unstable, then you can say, because this is the location of the eigenvalues of the matrix A, I can conclude that the equilibrium point of the nonlinear system is also unstable. Let us summarize this important result. Here is our nonlinear system, and we want to analyze the stability of its zero equilibrium point by analyzing the stability of this equilibrium point for the case of the linearized system. That looks like this. We can perform this analysis for the following two cases. Here's the first case. Let this be a complex plane, real part and imaginary part of a complex number. And let the eigenvalues of this matrix A be located strictly in the left half of the complex plane. That is, they cannot touch the imaginary axis or pass the imaginary axis. In this case, the equilibrium point x star is equal to 0 of the linearized system is asymptotically stable. Since this equilibrium point is asymptotically stable for the case of the linearized system, we can conclude that the same equilibrium point for the nonlinear system is also asymptotically stable. So asymptotic stability in the linearized case implies asymptotic stability in the nonlinear case. Second case. Let us assume that the equilibrium point of the linearized system is unstable. That is, the eigenvalues of the matrix A can be over here, can be, for example, over here, can be over here, or we can have one eigenvalue of the matrix A even touching the imaginary axis. However, other eigenvalues should not touch the imaginary axis. That is, we have at least one eigenvalue that does not touch the imaginary axis. Of course, you might have something like this. You might have an eigenvalue that's here and one eigenvalue that's here, and in this case, the equilibrium point of the linearized system is unstable. Since this is the case, we can conclude that the equilibrium point of the nonlinear system is also unstable. Let us summarize the second case once more. If at least one eigenvalue of the matrix A of the linearized system is in the right half of the complex plane, then the equilibrium point of the linearized system is unstable. This implies that the same equilibrium point of the nonlinear system will be unstable. In any other case, you cannot make strong conclusions about the stability of the equilibrium point of the nonlinear system by analyzing the stability of the equilibrium point of the linearized system. To illustrate this indefinite case, let us assume that the eigenvalues of the matrix A of the linearized system are over here. Obviously, the equilibrium point of this system is stable. However, it's not asymptotically stable. In this case, you cannot make any conclusion about the equilibrium point and its stability of the nonlinear system. The equilibrium point of the nonlinear system can be stable, unstable, asymptotically stable. However, you cannot make strong conclusions. Also, in this case, that is, in the case if we have two eigenvalues on the imaginary axis and one eigenvalue over here, we cannot make definite conclusions about the stability of the equilibrium point of the nonlinear system. This is also an indefinite case. So to summarize the indefinite case happens if one or more eigenvalues of the matrix A have zero real parts and no eigenvalues with positive real parts. The stability of the equilibrium point of the nonlinear system cannot be analyzed. So keep in mind this. Let's go back to our example. You will see in this video that the eigenvalues of the linearized system are on the imaginary axis. That is, the linearized system, or better to say, its equilibrium point is stable. And obviously, this is the third indefinite case. We cannot conclude anything about the stability of the equilibrium point of the nonlinear system by analyzing the stability of the linearized system. In this particular case, the linearized system is stable. However, you will see later on that the nonlinear system is unstable. Let's start with the analysis. We can easily show that the equilibrium point of this system is x1 is equal to 0 and x2 is equal to 0. I will show this in my follow-up tutorial. Next, let us linearize this nonlinear system. In order to linearize this nonlinear system, we need to compute the Jacobian of this nonlinear system. We can represent this system in this form. x1 dot is f1 and x2 dot is f2, where obviously this is f1 and this is f2. The Jacobian matrix of this system is defined like this. The first row of the Jacobian matrix are partial derivatives of f1 function with respect to x1 and x2, and similarly the second row is composed of partial derivatives of f2 with respect to x1 and x2. The Jacobian matrix has the following form: 3x1 squared plus x2 squared, then minus 1 plus 2x1 x2, 1 plus 2x1 x2, and we have x1 squared plus 3x2 squared. The matrix A of the linearized system is obtained by evaluating the Jacobian matrix at the equilibrium point x1 is equal to 0 and x2 is equal to 0. Once we substitute x1 is equal to 0 and x2 is equal to 0 in our Jacobian, we obtain this matrix A. 0, minus 1, 1, 0. Let us compute the eigenvalues of this matrix. The eigenvalues are the zeros of this polynomial, where I is the identity matrix and S is the complex variable. After some computations, we can see that the characteristic polynomial looks like this. If we set the characteristic polynomial to 0, we obtain the eigenvalues. The eigenvalues are obviously plus minus j, where j is the imaginary unit. Okay, obviously the equilibrium point of the linearized system is stable. This is because the eigenvalues of the matrix A of the linearized system are over here. They're on the imaginary axis. Now, in the sequel, I will demonstrate you that the original system is actually unstable. To do that, I need to erase this window, and for clarity, I will write my nonlinear system once more over here. I have minus x2 plus x1 squared plus x2 squared. x2 dot is x1 plus x2 x1 squared plus x2 squared. How to analyze the stability of this nonlinear system? This nonlinear system looks very complex at first glance, and we can, for example, try to apply Lyapunov's function. For example, we can try to find the Lyapunov function and then to analyze the negative definiteness of the Lyapunov function. However, this is a very difficult approach. There is a more elegant approach that can be used to analyze the stability of this system. And this approach relies on coordinate transformation. Instead of x1, we can introduce rho times cosinus theta. And instead of x2, we can introduce rho times sinus theta, where rho and theta are new state space variables. These are the polar coordinates. If this is our x1, x2 state space plane, we are basically saying the following. If this is the point on a state trajectory, we will represent this point by using this angle theta and this radius rho. These are the classical polar coordinates. The goal is to write this system in the polar form. That is, we need to write rho dot as some function of rho and theta dot as some other function, let's call it h, of rho and theta. Let's see how to do that. First, I will explain how to obtain this equation. From this equation and this equation, we can obtain x1 squared plus x2 squared is equal to rho squared. This follows from the fact that cosinus squared theta plus sinus squared theta is obviously equal to 1. Next, let us differentiate this equation. While differentiating this equation, we have to keep in mind that x1, x2, and rho are functions of time. And consequently, if we differentiate this equation with respect to time, we obtain 2 times x1 times x1 dot plus 2 times x2 times x2 dot is equal to 2 times rho times rho dot. Next, we need to substitute the expressions for x1 dot, x2 dot in this equation. By performing this substitution, we obtain this equation. 2 times x1 multiplying minus x2 plus x1, and instead of x1 squared plus x2 squared, I can simply write rho squared. Then we have plus 2x2 multiplying, let's see, what do we have, x1 plus x2. What do we have here? We have x1 squared plus x2 squared. We have rho squared again is equal to 2 rho times rho dot. Let us see and let us try to simplify this equation. By simplifying this equation, we obtain the equation that looks like this. 2 rho squared multiplying x1 squared plus x2 squared is equal to 2 rho times rho dot. I obtain this equation by simply cancelling this part over here. That is, if you multiply 2x1 times minus x2, you can cancel this term by the term obtained by multiplying 2x2 times x1. And what is remaining part over here, I have 2 rho squared from here, and I have in the bracket x1 squared, and similarly from the second term I have x2 squared. Obviously, this is rho squared. I will continue over here. As the result, I obtain 2 rho to the power 4 is equal to 2 rho times rho dot. I can cancel 2 and 2, and I can cancel this rho, and over here, instead of 4, I will have rho to the power 3. Consequently, the first state equation in new coordinates is rho dot is equal to the rho to the power 3. Next, let us determine the second equation. If I divide x2 by x1 from here, I obtain x2 divided by x1 is equal to sinus theta over cosinus theta. And this is tangent theta. From this equation, I can obtain the following equation. Theta is equal to arctan of x2 over x1. Next, let us compute the first derivative of theta. The first derivative of arctan function looks like this. It is 1 over 1 plus x2 over x1 squared times the derivative of x2 over x1. And the derivative of x2 over x1 is x1 squared, and over here I have x2 dot times x1 minus x1 dot times x2. After substituting the values from here, and the values for x1 and x2, and after rearranging the expression, we can obtain that theta dot is equal to 1. And this is our second equation. To summarize, our original complex system in new coordinates has a relatively simple form. Rho dot is rho to the power 3 and theta dot is equal to 1. Let us sketch the state space trajectories of this system. This is x1, this is x2. Let us assume that we start our journey from some initial condition, and let this be rho 0 and let this be theta 0. This is our initial condition, and we start our journey from here, and we want to see how the state trajectories will evolve from this point. Obviously, rho is always positive since the radius is always positive. So this first equation, since rho is positive, will tell us that rho dot will always be positive. This means that rho will increase over time. And what happens over here? Theta dot is equal to 1. This means that we will go in the mathematical positive direction. That is, theta will increase. This implies that our state trajectories will look like this. They will increase. The radius will increase over time. This is because the first derivative of rho will always be positive, and we will move in the mathematically positive direction, that is, in the counterclockwise direction. Similarly, if we start from here, let's choose another color, the trajectories will look like this. This implies that the equilibrium point is unstable. And this is the main conclusion of this example. To repeat, the linearized system, that is, its eigenvalues were on the imaginary axis. This implies that the equilibrium point of the linearized system is stable. However, we have seen that the nonlinear system is unstable. Okay, that will be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.